In 6.2, we're multiplying and dividing radical expressions. So just to note, again, in this lesson, we will assume all variables are positive, which means you don't have to worry about the absolute value sign or dividing by 0. So in other words, if I take the fourth root of x to the fourth, if x is a positive number, we can just say those cancel each other out and we'd be left with x. If the variables were negative, you get something like this, and you'd have the fourth root of negative 3 to the fourth power is 81, and the fourth root of 81 is 3. So if this were a negative number, these wouldn't quite just cancel each other out and leave you with negative 3. It actually leaves you with the absolute value of negative 3. And then that causes some other problems that we're just not going to worry about in this section. So assume all variables are positive, and that something like this, the fourth root of x to the fourth would just be x. So with that being said, first example, simplify the radical expressions. Now we've done stuff like this before. We've simplified the fifth root of 64. We've looked at simplifying things like the fifth root of x to the 10th. But if I combine these things, here's the note. If the exponent on the variable is higher than the index, so if this is higher than 5, then the expression is not simplified. If the constant or the number, 64 in this case, if that has any perfect fifth factors, then this expression also isn't simplified. So here's where we're going to go with this. If I factor 64, well, 64 does have a perfect fifth factor. So think about your perfect fifths. 2 to the fifth power is 32. So I could break this expression down and say the fifth root of 32 times the fifth root of 2 would be the same thing as the fifth root of 64. If I'm looking at simplifying this, so that 8 is higher than 5, which means I'm going to have to simplify further, I'm going to break this down into the fifth root of x to the fifth. So 5 divides evenly into 5, and then if I had x to the 8th, fifth root, I would have 3 more x's left over. So this is your fifth root of x to the 8th term. And then that y term, if you notice, the exponent on y is smaller than 5, so I'm just going to leave that as the fifth root of y to the 4th. If I clean this up, fifth root of 32 is 2. 2 to the fifth power is 32. Fifth root of 2, that wouldn't be a nice integer, so I'm just going to leave that. The fifth root and the fifth power, those cancel each other out. Remember, this is just like saying x to the fifth to the 1/5 power. So that would be x. And fifth root of x cubed. And then I have a fifth root of y to the 4th. So I'm going to look at these terms that are outside of the radical sign. Those are going to go out front. And then anything that's left under your fifth root is going to stay there. So I have fifth root of there's a 2, there's an x cubed, and there's a y to the 4th. This is your most simplified answer. Note that my exponents under the radical sign, both of these are smaller than 5. So if you think back to our exponent review, well, radicals have the same properties of exponents. Because if I take, the cube root, that's the same as if I raise something to the 1/3 power. So all of those properties of exponents, things like this, if I have 4 times 3, the quantity squared, well, I could say, as long as I'm multiplying, I could say that's the same as 4 squared times 3 squared. If I have something like this, xy to the 5th power, I'd have xy times xy times xy times xy times xy. That'd be the same as if I said x to the 5th times y to the 5th. So same here for radicals, and this is really what we were doing on the last example, right? We said, well, if I have the square root of 20, I could say that's the same as the square root of 4 times the square root of 5. We could do the reverse. If I have the square root of 4 times the square root of 5, as long as your index is the same, you can combine these and say, okay, well, this is the same index, the square root of 4, square root of 5, your index is 2. I can multiply those and combine them into one expression, say the square root of 20. So same thing here, as long as your indices are the same, This would be like x to the 1/3 times y to the 1/3. As long as your indices are the same, it's perfectly legal to multiply these and say it would be like x times y to the 1/3 power. And that's kind of, again, utilizing this property of exponents. So just a quick check. Think about, could you combine these radicals? So maybe pause the video, give this a thought. The middle one is really what I was just talking about on the previous page. So if I have the same index, you can certainly combine these and say cube root of 4 times -2 or the cube root of -8. Now, why is this useful? Well, I don't know what the cube root of 4 is. It's not an integer. I don't know what the cube root of -2 is. But if I multiply these, I certainly know that the cube root of -8 is -2. Now, on the bottom in the pink, this is really what this is saying. Here is how your radicals relate to those exponent properties. The first one, you can't combine this. Your indices aren't the same. So this is like 6 to the 1/3 times 2 to the 1/2. Indices are not the same, can't combine. I couldn't really go any further with this. The last one you're adding, this is also something that you can't combine because you're adding the expressions. So in a previous lesson, I think we talked about how this was totally illegal because you're adding the radicals. So I cannot just add and say square root of 13. So this can't combine. Yeah, I have the same indices, but I'm adding them, not multiplying. This would also be similar to why you can't say this. So I cannot say this is x plus 5 squared. So sure, my exponents are the same, but I'm adding these terms. I can't combine those. You'd actually have to FOIL this. This should be what, x squared plus 10x plus 25, not x squared plus 25. So if I have the same indices and I'm multiplying, I can certainly combine those radicals. So that's going to help us on a problem like this. If I ask you to simplify, again, do I know what the cube root of 6 is? Not really. Do I know what the cube root of 12 is? I mean, I could estimate it'd be 2 point something. But if I combine these, so I have the same indices, I multiply, I could combine these under one radical. So if you want to do that, maybe pause the video and multiply these together. Let's check if we get the same thing. So if you multiply 6 times 12, 72, x to the 5th times x squared gives you that x to the 7th, and y to the 4th, y to the 10th gives you y to the 14th. So I'm taking the cube root of all of this stuff. And now from here, so I multiplied it, this should allow me to simplify a little bit nicer, because I'd be thinking, are there perfect cube factors of 72? So start listing your perfect cubes, 2 cubed, 3 cubed, 4 cubed, and it looks like, yep, 8 is a factor of 72. So from what we did in previous examples, maybe pause the video and see if you can come up with the most simplified form for this expression. So 8 is a factor of 72, 8 is a perfect cube. So 8 times 9 is 72. And then, if you were looking at simplifying this exponent 7 is higher than your index 3. So you'd want to be breaking this down. So at this point, you might be thinking, well, I want to break this down into groups of 3. So I have one group of 3x's, another group of 3x's, and then I'd have another x. So 3x's, one more. Total, that would give you the 7x's. Here's another thought, though. Instead of doing something like this, which might become kind of complicated when you're looking at y to the 14th, I'm just going to get rid of this and write it as the cube root of y to the, or cube root of x to the 6th. So kind of a shortcut is, if I break this x term down into the largest multiple of 3, that's still smaller than 7. So 3 divides evenly into 6. And then I'd have 1x left over. That might make things a little bit easier. So by following that same thought with the y, let's see, 3 goes into 14, what, 4 times? Oops. So I'd have the cube root of y to the 12th, 3 times 4. And then if I want 14 y's, I'd have 2 y's left over. So 12 is a multiple of 3. 3 should divide evenly into 12. And then here's what's going to end up happening. So cube root of 8 is 2. And then you have that cube root of 9. This, remember, this is like x to the 6th to the 1/3. So 6 times 1/3, or 6 divided by 3, that would just be x squared. And then I'd have that cube root of x still. Can't simplify this because that exponent is smaller than the index. And then this is like y to the 12th to the 1/3. So 12 times 1/3, or 12 divided by 3, would be y to the 4th. And then you'd have that cube root of y squared. So your final most simplified answer, anything that was outside of the radical, place out front. So you have a 2, you have an x squared, and you have a y to the 4th. And then anything left under the radical, you have a 9, you have an x, you have a y squared. This is your most simplified answer because there are no perfect cube factors of 9, and your exponents on the variables that are under the radical are smaller than the index. Now I want to point out another way to arrive at this same answer. If you like the factor tree, you could go that route. If I'm looking for the cube root of something, then when you make the factor tree, cube root of 72, any groups of 3 would go out front. So there should be 1, 2 out front. Anything left over that doesn't have a group of 3 would be left under the radical, so that 3 times 3 would give you the 9. And if you're thinking about the x to the 7th, you'd be looking for groups of 3 also. So this would be 1 x would go out front. For this group of 3, another x would go out front. So there should be 2 x terms out front. And then there'd be 1 left over under the radical. And you could do the same thing for your y terms. So if you're multiplying radicals with the same indices, you can combine them. If you're dividing radicals with the same indices, you can also combine those. And it's the whole idea why something like this would work. So from your exponent properties, this 1/2 will kind of be attached to everything. It'd be attached to all of these, be attached to everything in your denominator. These, whatever's on the left side here, is equivalent. This is equivalent to this. And remember, the 1/2 power is just like saying the square root. So this is the same as saying this. As long as my index is the same, if I'm dividing 2 radicals, I can combine them into 1 radical. So if I look at this one here, again, I might not know what the square root of 18 is. It's not a nice whole number, it'd be 4 point something. I don't know what the square root of 2 is, but if I combine these under 1 radical, 18x to the 7th over 2x cubed, I would get the square root of 18 divided by 2 is 9. X to the 7th divided by x to the 3rd is x to the 4th. 3 x's on the top would cancel with 3 x's on the bottom. And square root of 9 is 3. Square root of x to the 4th, or x to the 4th to the 1/2 power, would be x squared. 3x squared times 3x squared would give me 9x to the 4th. So with this idea, last example, pause the video, see if you can combine everything that we've talked about in this lesson and simplify this radical expression. So first step, I combine these under 1 radical since these have the same indices. 96 divided by 2 is 48. Y to the 26 divided by y to the 3rd is y to the 23rd. And then I did move this to the top of the fraction, so I could write that exponent and make that exponent positive. And then from here, you'd want to look to break it down. So are there any perfect 4th factors of 48? Well, sure. 2 to the 4th is 16. So I could write this as 4th root of 16 times 4th root of 3. And if you're looking at this, instead of writing a bunch of groups of 4, well, 4 divides into 20 evenly. So 20 is a multiple of 4. So I'm going to write this as y to the 20th. And then I have 23 y's, so I'd have 3 left over. And then that x term is fine because your exponent on x is smaller than your index. 4th root of 16 is 2. Y to the 20th to the 1/4 power. So this is like saying this. 20 divided by 4 would give you 5, so y to the 5th. And then everything else would just stay under that 4th root. So this is your most simplified